Enterprise IT faces a constant tug of war. Organizations want the agility to build modern REST APIs, but they simply cannot afford to risk the unyielding stability and reliability of their core mainframe business logic. Moving data off the mainframe or building external network bridges to reach it creates a massive bottleneck. Every time a web application requests data over a network hop, you add latency and complexity to a system that was built to execute millions of transactions per second. To solve this, IBM introduced CICS Liberty. This is a hybrid architecture that embeds a Java application server directly inside the mainframe environment. By co-locating modern Java microservices right next to traditional COBOL programs, you eliminate inter-platform communication latency. This setup also provides a distinct financial advantage. Java workloads running on ZOS are eligible to be offloaded to ZIIP processors. ZIIPs, or Z Integrated Information Processors, are dedicated specialty engines that execute Java code without consuming general-purpose computing cycles, which directly reduces your software licensing costs. Modernizing an enterprise system doesn't require discarding decades of proven, highly optimized COBOL logic. You only need to build an in-process bridge to expose that logic to the modern web. Let's look at exactly how that bridge is built. This diagram shows the architecture of how CICS supports a Liberty Java Virtual Machine, or JVM. Notice the boundaries. The Liberty server does not run as a standalone external process. It operates directly inside the CICS region itself. Within that region, CICS creates a language environment enclave. This enclave is a standardized ZOS runtime structure that hosts the Liberty JVM natively, ensuring the Java environment operates under the exact same system controls as your legacy programs. When a web client sends an HTTPS request, the traffic flows directly into the Liberty JVM's JAX-RS component. JAX-RS is a Java API specification used to create RESTful web services that communicate via the HTTP protocol. Here is where the integration happens. The Java application uses the JCICS API to directly invoke the COBOL program. JCICS is a set of Java classes that provide native access to CICS resources, like programs, files, and queues. Because both programs share the same address space, the data moves instantaneously. Running both environments under one roof is the specific mechanism that guarantees sub-millisecond latency. Because CIS orchestrates the entire flow, both the Java and COBOL layers share the same unit of work, allowing for guaranteed transaction rollbacks if any single step fails. Step 1 in standing up this architecture is securing the environment. To initialize the JVM server safely, a developer must modify 3 vital configuration files. First, you define the JVM server resource. Within this definition, you must set a thread limit. This parameter governs exactly how many concurrent Java threads can execute at once, preventing a sudden spike in web traffic from exhausting CPU and memory required by other CIS programs. Second, you configure the memory boundaries. Inside the jvm.options file, you set the initial and maximum heap sizes using the XMS and XMX flags. This ensures the Java environment has enough memory to run, but cannot overconsume region storage. Third, you configure the application server itself. Inside the server.xml file, you activate the specific Java features your application needs, like the JAX-RS 2.1 feature for REST support, and define the default HTTP port that will listen for incoming traffic. Finally, you establish the routing rules. You create a URI map resource to map incoming web traffic from a specific URL path, explicitly routing those requests directly to this newly defined JVM server. These precise resource constraints and routing rules are mandatory. They ensure your new Java microservice behaves as a well-governed citizen that processes modern web requests without destabilizing the wider CICS ecosystem. Now that we have the server configured, we can look at the code. The Java microservice class is built as a standard JAX-RS post endpoint designed to receive data parameters from a web form. Inside that endpoint, the Java code calls the CICSFactory.createChannel method. This creates a structured data channel and packs the incoming web data, like a customer ID and an amount, into distinct CICS containers. With the data packed, the Java application initiates the execution trigger. It uses the program.link method, passing the channel object and directly targeting the legacy COBOL receiver program by its exact name. On the other side, the COBOL program wakes up. It uses exact-cics get container commands to open the channel and extract the payload from the Java layer, pulling the customer ID and amount straight into its own variables. This integration relies on an exact data contract. If the container string names do not match perfectly between the Java sender and the COBOL receiver, the data transfer will silently fail. Precision here is required. Once the code is written and verified, we move to the deployment phase. The development team compiles and packages the Java service into a WAR file using a build tool like Maven. A WAR file, or Web Application Archive, is a jar file used to distribute a collection of Java server pages, Java servlets, and other resources into a web server. To deploy the application, you transfer that WAR file into the liberty/dropins/directory located in Unix System Services. Liberty actively monitors this folder and triggers an automated deployment the moment the file arrives. With the application in place, you initialize the server from the mainframe terminal. Running the CEMT set JVM server start command boots the Liberty runtime and loads your microservice into active memory. Be aware of a common operational pitfall. If you update the underlying configuration files, like the server.xml, Liberty will not absorb those changes automatically. You must manually restart the JVM server via the CEMT interface to apply them. Finally, we run the integration test. From a command line, you execute a curl post request, sending a test customer ID and transaction amount directly to the mainframe's HTTP port. When your terminal returns a successful HTTP 200 response, the loop is complete. You have successfully updated a legacy dataset via a COBOL program triggered entirely by a modern web client. You now have a working, high-speed REST API. The seamless execution of this request proves that mainframe data can flow into modern applications instantly, without the drag of external networking. The immediate next step for scaling this into production is security. You must lock down the new Liberty endpoint by integrating it with the mainframe's native RACAF security protocols. RACAF, or Resource Access Control Facility, is the primary security product for IBM's Z OS that provides identification, authentication, and authorization for system resources. You should also review your System Management Facility, or SMF records. SMF is the Z OS component that collects and records system-level performance data for accounting and analysis. These logs will validate your performance metrics and verify the exact CPU cost savings generated by your ZIF processor offloading. Mastering CICS Liberty provides development teams with a repeatable blueprint. They can now innovate and scale their most critical systems without risking operational disruption.